Today we're diving into a fascinating and honestly pretty scary system failure. It's called a retry storm, and it's a perfect story of how good intentions in code can go spectacularly wrong, turning a system's own survival instinct into its worst enemy.
Just let that sink in for a second. This whole story kicks off not with some massive cyber attack or a catastrophic bug, but with a tiny 5-second flicker in the network. A blip. But that blip triggered a total system meltdown. Why? Because the real threat was already inside the system.
Now, for the users on the outside, the problem was simple and super frustrating. All they saw was this: 503 service unavailable. That's it. Payments were failing, the app was basically useless. But behind this one little error code, a much bigger, much more complicated disaster was unfolding.
On the inside, it was absolute chaos. The database CPU was slammed, just pinned at 100%. This wasn't just a slowdown. The system had hit a solid brick wall. The impact on the business was immediate and brutal. Thousands of payments failing every single minute. And as you can imagine, customer support was just flooded with people wanting to know what was going on.
So let's start digging in. The impossible system collapse. I mean, that's what it felt like to the engineers on call. They were staring at this central, baffling question. How on earth does a tiny, temporary glitch cause a complete hours-long disaster? The math just didn't add up.
And this is where it gets really weird. Check this out. On one side, you have the cause, a 5-second network hiccup. That's nothing. It's the kind of thing that happens all the time. But on the other side, you have the effect, a 2-hour, full-blown outage. The two things were so wildly out of proportion, it defied all logic. All right, so with the whole system on fire, the team did the only thing they could do. They dove into the logs. I mean, this is the system's black box, the only source of truth they had. They knew it was going to be like finding a needle in a haystack, but somewhere in those millions of lines, there had to be a clue. This was the #1 question they had to answer. The system was acting like it was under a massive denial of service attack, just completely overwhelmed. But when they checked the monitoring dashboards, the number of actual users hadn't changed at all. So if it wasn't the users, where in the world was all this traffic coming from?
And then they found it. The logs revealed something absolutely chilling. The traffic wasn't random. It wasn't organic. It was coming in these perfect synchronized waves. Look at this timeline. At 10 a.m. in 2 seconds, boom, 10,000 retries. 2 seconds later, boom, another 10,000. And on, like clockwork. This wasn't an attack from the outside. It was a perfectly coordinated rebellion from their own client.
Now, this whole phenomenon has a name, and it's one that gives systems engineers nightmares. It's called the thundering herd problem. The team had finally identified their culprit. The system wasn't being attacked by some external enemy. It was literally stampeding itself to death.
So let's break down what that actually means. Think about that 5-second network glitch. When the service finally came back online, that recovery acted like a starting pistol in a race. Thousands of disconnected clients all heard it at the same time. They were all programmed with the same, simple, well-intentioned logic. Oh, it's back. Let's try again. And they all tried again at the exact same millisecond, creating a tidal wave of traffic that the newly recovered service just could not handle.
And really, this says it all. The platform DDoSed itself. The very piece of logic that was designed to make the system resilient, that helpful little retry button, had become the weapon in a massive self-inflicted attack. It's the classic case of the cure being way worse than the disease.
Okay, quick pause. If you've ever spent hours, maybe even days, chasing a ghost, a bug that just disappears the second you think you've cornered it, you know the pain. If you get something out of these engineering war stories, do me a favor and subscribe.
All right, so identifying the problem is half the battle. But now for the really clever part, the solution. How do you tame a stampede that's literally programmed into your system? You can't just tell thousands of clients to calm down. You have to fix a behavioral problem with a smarter architecture.
And that smarter architecture is a beautiful 2-part strategy. First up is exponential backoff. That just means clients wait a little longer between each failed attempt. Second, and this is key, is jitter. That's adding a tiny bit of random delay. Together, these two things have one critical job: to break the synchronization, to break up the herd. Let's put this side by side. On the left is the old, naive way, a fixed 2-second delay. Simple, predictable, and as we saw, totally deadly. On the right is the smart retry. First, exponential backoff kicks in. You fail, you wait 2 seconds. You fail again, you wait 4, then 8, and so on. But, and this is the secret sauce, jitter adds a little randomness. So instead of everyone retrying at exactly 8 seconds, they try at 8.1 or 7.9 or 8.3. They get spread out.
And the result? Well, it's dramatic. The difference is night and day. The naive retry gives you that terrifying red spike, that wall of traffic that crushes your server. The smart strategy with backoff and jitter, it transforms that spike into a gentle, manageable blue wave. The total number of requests is exactly the same, but now they're spread out over time, giving the system a chance to actually breathe and do its job.
So what's the big lesson here? What's the takeaway? It all comes down to building the principle of patience directly into your system's architecture. It's about shifting your mindset from demanding an immediate response to allowing for a graceful, calm recovery.
So the new normal for this system is one that just knows how to wait. When a service has a problem, the clients don't panic, they back off, they give it some space, they try again later, but at slightly different times, and the result is a beautifully stable recovery with almost zero chance of that synchronized collision ever happening again.
And this brings us to the most important engineering principle from this entire story. Look, in any complex system, failure is going to happen. Components will go down. That's a given. True resilience isn't about preventing every single failure. It's about how you manage the recovery. Because systems don't fail when they go down. They fail when they try to come back up the wrong way.
If you want to understand the deep principles behind the code and not just the syntax, make sure you subscribe. We've got plenty more deep dives like this one coming up. Thanks for watching.